I can't see you, I can only hear you. Can you see this? Okay, thank you. So, hello? Can you see my title slide? Yes? Okay, thank you. All right, so it's a delight to be with you today. However, virtually, I apologize profusely for not being able to attend in person, but I hope to meet a lot of you at the same event next year. This is a really important topic. We've already heard this morning about many different issues. And so this is a study where we're looking at what can our dietary component do to breast cancer risk. And so I have a disclaimer. I am co-founder and vice president of the Anti-AGEs Foundation. That sets me up really nicely for what our age is. So we call them advanced glycation end products, or AGEs for short. And so these molecules form a non-enzymatic reaction when a carboxyl group from a sugar combines with either a protein or lipid or a DNA on an amine group, and this undergoes non-enzymatic reaction, which is reversible at different stages. But when it finishes the process, it forms an advanced glycation end product. And this product at this point is irreversible. And I will call these AGEs. So why are they important and why do we care? So AGEs damage our bodies. So they can cause protein cross-linking. They can cause mutations when they bind with DNA. And they can also bind to certain receptors and set off a bunch of intracellular signaling cascades, which lead to aberrant signal processing. And this is just a visual representation of what AGEs do within our bodies. And so as we age, we all know that we start to get wrinkles. And so wrinkles in your skin are AGEs cross-linking of collagen. And so if you can imagine this happening to every organ in your body as you age and prematurely age, as we consume more and more AGEs. And so why, again, is this important? So AGEs have been linked in the literature by many, many groups other than ours with many chronic diseases, which are listed here. But importantly, the 4 horsemen of death is what we call them. So looking at heart disease, diabetes, Alzheimer's disease, and of course, our special interest, which is cancer. And so all foods contain AGEs, right? So every single product that we eat contains a certain amount of AGEs. And I give these values in 3-ounce portions. However, for those of you who are in the metric system, this is about 100 grams. So I normally present in America, so they do the ounces system. So carrots have about 12 units of AGEs. White fish can have about 450 AGEs per portion, and then chicken can have about 800 units. And these are all raw products. And so these cause, when we eat them, we get AGEs in our body. And when we eat them and they're preformed, they're immediately available for damage, as I described on the earlier slide. What's important to note is that cooking actually increases AGEs. So they're promoted by the cooking process. So an example that we like to give is if you have a raw steak, it contains about 800 units of AGEs. And if you put this into like a stew or a slow, moist heat, it goes to about 2,500. However, if you put this in a pan and either grill it or fry it, it goes to around 8,000 units. And so this leads to the ever accumulation of AGEs when we're eating them on a daily basis. Food processing also increases AGEs. So when foods go through the food processing of the manufacturing process, they actually add AGEs to their products in order to enhance taste and appearance. And so tofu, a very popular vegetarian option, is actually a very synthetic product and contains about 800 units of AGEs, and this is before it's cooked in any way. Cheeses are very popular, have around 8,000 units of AGEs. And then, of course, cereal products, which we all know are a very processed product. We give the example of Rice Krispies here, having about 2,000 units of AGEs. And again, when we consume these, it leads to increased accumulation within our body, which increases the aging process. And so how is this related to breast cancer? And so we collaborated with the investigators shown here, Dr. Steck from the University of South Carolina, Dr. Peterson from Washington University, and Dr. Turner, one of my colleagues here at Virginia Commonwealth University. And they have published together 3 large data set epidemiological studies where we took the data sets from published data population studies developed an algorithm in order to calculate the amount of ages that are present within foods based on food frequency questionnaires. And Dr. Uribarri's paper that he published in 2010, which contains about 500 foods and their age levels. And then we searched on a breast cancer registry to look at incidence and cancer outcomes. And so the first study was published in 2020 using a PLCO study and showed that basically we took the amount of ages that women ate and divided them into quintiles. And we found that the women who were eating the highest amount of ages in their diet had increased risk of breast cancer. So more women were getting breast cancer. And then the second study, which was the AARP study, which was also published in 2020, we actually looked at breast cancer phenotype. And so we found that the women who were eating the highest amount of ages had more aggressive disease. And then the third study was a WHI study where we looked at mortality rates and found that published in 2021, that the women who were eating the highest amount of AGEs in their diet had increased risk of mortality. And this was all major causes of mortality in the women who received a diagnosis. The manuscript that we have in preparation right now, which is the one that I've been associated with in this group, is then these studies have been mainly correlative because they're food frequency questionnaires. And so what we did is we took from women with breast cancer and looked at circulating levels of AGEs, which we can measure by multiple methods. And we found that women who had the highest levels of circulating AGEs in their system had decreased overall survival, recurrence-free survival, increased breast cancer severity score, and distant metastasis-free survival. And this is a wheel study, and we'll be hopefully getting this out towards the end of this year. And so that's all very interesting, but why are we interested in women with, young women with breast cancer and this very important topic? And so we know that the lifetime risk of breast cancer is pretty much established during puberty. And so we wanted to set up a model where we could assess the impact of dietary age consumption during puberty and the impact on the developing gland and breast cancer risk. And so this is our mouse model that we use. So we use FEBN and Black 6 mice. I'm only going to show you the FEBN data today. And so these are the diets that we assign to them when we wean them at 3 weeks of age. So the regular diet is just a regular mouse chow that you'll find in most standard mouse facilities, at least in the US, where the carbohydrate source is made up predominantly with starch. And we call this the control diet, or the regular diet. And then our low age diet, we call it low age because although it doesn't have a really high age content, it has high sugar. So the carbohydrate source in this case is mainly glucose. And this can be converted into ages within the body through the endogenous normal process. And then we take this low age diet and we actually autoclave it for 120 degrees at 120 degrees for 15 minutes and drive the non-enzymatic glycation reaction. And we have increased amount of AGEs in this diet. And then we feed this diet to the mice at 3 weeks. And then we sacrifice them at either a pubertal time point, which is at 7 weeks, and the adult time point, which is 12 weeks. And obviously we weigh the amount of food that they eat and the weight the animals. And we find that there's no real differences in weight at this time point. And the amount of food that they consume is equal across all of the diets. So they don't eat more than one than the other. And so what we found is that dietary age consumption delays ductal outgrowth and increases ductal branching. So these are just representative whole mounts with the arrow indicating the amount of extension. So as a woman develops her breast, the ductal network expands throughout the fat pad to create the ductal tree and laying the foundation for when she gets pregnant so she can produce the structures in order to feed the baby. And so you can see here, I think I appreciate in the black bars that we see a decrease in ductal extension at the regular time points. However, this is a delay in extension and not a complete inhibition, as it does catch up at the 12-week time point, which is our adult time point. And I think also you can appreciate here that there's an increase in branching in the mice that are fed the high age diet. And this is sustained throughout the adult time point. And the increased branching has implications density in the mammary gland, which we know increased density is associated with increased risk. The other things that we look at are these terminal end buds, which were alluded to in the previous talk with Dr. Prakash. And so we looked at both the size of the terminal end buds or tabs, as well as their number. And you can see that the tabs that we observed in the high age diet were much larger and they were greater in number. what was really interesting is at the adult time point where these terminal end buds are supposed to have regressed to terminal end ducts, we still see structures that resemble these larger club-like structures, although we don't call them tabs, we call them tab-like structures. And importantly, they're still present if you take the mice out to the 7-month time point. And these are thought to be the initiating sites for tumor development. And so this obviously is an issue that they're still present. They're also proliferative structures, so they are quite proliferative in general at the point where they are progressing through the gland, as you can see in the white bar here. However, we do see increased proliferation in the mice with the high-age diet, and at 12 weeks when they're supposed to have regressed, they're still quite proliferative. And this is just a representation of how they look from an H&A. So this was all whole mouse previously. So this is what a regular tab will look like. So it has a teardrop structure with stroma around the neck of the tab. So this would be the direction of movement. However, you can see in the high-age diet, it's a lot more cellular. There's a lot more stromal surrounding the entire tab, not just at the neck. And then when we had a pathologist look at these structures, we found that there were cells that appeared to be macrophages and fibroblasts, which are not normally present at the tip of the tab. And we've since done spectral staining with markers for macrophage and fibroblasts to show this, but I'm not showing it today, but this data is published. And then, as I was talking earlier, they do have proliferative structures. So this is proliferation at the tip of the tab and the direction of movement. However, in the high-age diet mouse, you can see that the proliferation is throughout the entire tab. And then when we zoom in the stroma, you can see there's actually proliferating cells also within the stroma. And we quantified that here where we see increased proliferation in the stroma surrounding these highly active tab-like structures. And then we also see this in the ducts. So this is just a cartoon. I'm sure most of you have seen this before, where you have a normal breast has a single myoepithelial layer surrounding a single luminal epithelial layer. And we see fibroblasts and macrophages within the extracellular matrix surrounding the ducts. However, when you start to get a DCIS, which is an early pre-lesion for breast cancer, you see a filling in of the lumen and then increased recruitment of macrophages and fibroblasts within the microenvironment. And then these are duct examples from our mice, where you see this normal regular duct, which looks like the picture on the left. Whereas we see structures like this in our high-age fed mice, where we see the filling in of the lumen. And then when we stain these with our proliferative marker Ki67, you can see they're highly proliferative structures. And so this is quantified down here, where we see increased proliferation in our ducts. This is illustrating the quantitation of the abnormal duct morphology, seeing an increased abnormal duct penetrance within our high-age fed mice. And then also this is sustained through the 7-month time point. And so I talked about the infiltration of the stroma. And so we think the stroma is really playing a big part in driving this epithelial phenotype for our AGEs. And so what we did is we isolated our fibroblasts from our mice that were fed the high-age diet at the 7-week time point. And we looked at a series or a panel of markers that are associated with an activated fibroblast phenotype, which is illustrated here by both qPCR and Western blot. And then we set up a co-culture system. And so here what we do is we have a transwell co-culture system where we have our epithelial cells in the top insert, and we're measuring here the movement of the epithelial cells or epithelial cell migration. And then in the lower chamber, we have either AGEs that we've added ex vivo, or we place fibroblasts in the bottom and then treat with AGEs. And so I think you can appreciate here that when we have our fibroblasts do promote epithelial cell migration, just as being a normal fibroblast. But when we take our fibroblasts from our mice fed a high-age diet, there's an increased epithelial proliferation, suggesting that they're slightly more activated. And then when we treat our bottom lower chamber with AGEs, we don't see any increase in epithelial cell movement in the absence of fibroblasts. But when we add AGEs to the fibroblast chamber, we see an increase in epithelial cell migration over that untreated control. This is important that we think that fibroblasts are responding to the AGEs to crosstalk with the epithelial cells to make them more aggressive, because when we put our AGEs here in the upper chamber on top of the epithelial cells, we do not see this increase in epithelial cell migration, suggesting it is a fibroblast Parker mechanism that we're observing. And so I don't know if I mentioned already that there's a receptor for age called RAGE. It's the most well-studied receptor for age, although there are others. And so it's been published in different large data sets that RAGE is not present in the normal mammary gland. And when we look at the total mammary gland ourselves by Western blot or qPCR, we do not observe RAGE expression. However, if you isolate fibroblasts from the mammary gland and then probe for RAGE, you do see it in the normal mammary fibroblasts. And we do increase expression in the fibroblasts isolated from mice for the high-age diet. That's illustrated here by Western blot, as well as ELISA in qPCR. And so we wanted to know whether this fibroblast RAGE was important in order for promoting this age-mediated epithelial cell migration. And so we took our RAGE null mice and we did the same co-culture transwell insert assay and found that when we added age to the fibroblasts in our transwell migration assay, it did not promote epithelial cell migration when RAGE was not present, as you can see here on the right-hand side of this epithelial migration blot. And so why is this important for tumor growth? So this is my last data slide, looking at whether or not dietary ages promote aggressive tumor growth like we saw in our epidemiological studies. And so this is the same schematic where we take our mice at 3 weeks, we wean them onto the diets, then we do our tumor injection. So this is an orthotopic tumor injection with MET1 tumor cells, which is a mouse syngeneic likened to be triple-negative breast cancer cell line. And then 3 to 4 weeks later, we look at the size of the tumors. And what we find, if you can see here in the blue line, is how a regular tumor would normally grow. And then mice for the high-age diet, this is the trajectory. So we're promoting more aggressive tumor growth, suggesting that the environment of the mammary gland is responsible for this tumor growth. We did this in the RAGE null mouse. In the RAGE null mouse, not a single cell within the mouse has expression of RAGE. However, I will mention that the tumor cells that were injected do express RAGE. And we see that in the black circles, this is like the growth of the normal tumor within the mice. When both alleles of RAGE are present, you can appreciate in the black squares here that when we lose one allele of RAGE, we see a reduction in the ability of the tumor to grow. And then we take the RAGE null mice, you can see down here in the triangles, you completely ablate any tumor growth when the mouse is null for RAGE, even though the epithelial cell, tumor cells that we're injecting do have RAGE expression, suggesting that there's a strong stromal influence here on tumor growth. So what can we do? Obviously, by being aware of what AGEs are and how they contribute to chronic disease, we can make small changes in our daily lives, which will reduce the amount of AGEs that we accumulate. The ways in which we can do this: avoid foods that are high in protein, sugar, and fat, which are the base molecules for the age formation, as well as processed foods. Everyone's heard that message a million times, so that I try to focus more on the cooking side of things. So change how you cook your food. So you can cook your foods at lower temperatures for longer, for example, a slow cooker. You can cook over ceramic surfaces instead of metal. You can substitute unhealthy marinades with lemon juice or vinegar. It inhibits the age formation during the actual cooking process. In addition, we recommend skipping the browning step when you're preparing dishes such as stews or rolls. So just stick your meat straight in. You exercise regularly. This can also lower the level of AGEs in the bloodstream, which helps prevent accumulation. And then I always like to leave everyone with a final thought, that if our children eat 3 or 4 meals a week that are low in AGEs, over a lifetime, this can have a significant impact on their overall health in later life and prevent the onset of chronic diseases, including breast cancer.